Okay, welcome guys. We're going to start the earthquakes lecture. And so in this particular lecture, I want to say series, we're going to talk about what causes earthquakes. We're going to talk about the distribution of earthquakes, the damages that they cause and how we track them, and how we were working to predict them. And we'll also talk about what we've actually learned from them. So when I get back, I'm going to ask if anyone has experienced an earthquake. So a heads up on that one. But we are going to just look a little bit at some of the damage that earthquakes can have. There's this one here is sorry, I have the wrong thing on. So this one here is from Anchorage, Alaska. This one here is from California. If you've been watching the news, there's been a lot of information about the recent earthquake in Morocco. And so I may try and add a little bit of that when I get back. This one here is from Istanbul. And this one is San Francisco, a long time ago. We'll talk about this particular instance because it does have some important historical impacts on our understanding of earthquakes. So, definition for an earthquake, and it would be up here if the system was cooperating with me, but it's not, so that's okay. So, an earthquake is the vibration of Earth produced by a rapid release of energy. They often last for less than 1 minute, and you're going to hear me say that a couple more times in this particular lecture series. So why do earthquakes occur? Well, it depends on who you ask. According to natural theology, which was prior to the Enlightenment in the early 1700s, earthquakes were actually God's way of punishing humans. According to intelligent design, they were designed to allow humans to understand the structure of the earth. And according to science, they are the result of ruptures or slippage along fractures in the Earth's crust. And these fractures in the Earth's crust are called faults. Okay? So faults are ruptures, are fractures in Earth's crust. So a great example is along the where is our plate boundaries, but there's lots of other examples that we'll talk about later. So we have a little diagram here, and we have some terminology we're going to work on. So we're going to start with this one here. This is our focus. And the focus is the source of the energy release. Okay? They're generally somewhere between 500 and 700 kilometers deep. Now, if we go directly up from our focus, we reach what is referred to as the epicenter. And so the epicenter is directly above the focus on the surface of the Earth. Sorry, I'm running out of space here. And so, sort of like if you take a pebble and you throw it into a pond and you see these ripples that come out because you've disturbed it, when an earthquake occurs, you have these ripples that go out, but they're spreading out throughout the rock. And so you notice these ripples that are coming out. And this is energy, and it is referred, and these are called seismic waves. Okay? This energy dissipates very quickly, but we can detect this energy using what is called a seismograph. Okay, so seismographs are really just sensitive equipment, and it measures seismic waves. There are over 30,000 earthquakes that occur annually, every year, worldwide, and they're strong enough to be felt. But most of them are really just minor. They're not really a big deal. Give me a sec. So only about 75 significant earthquakes occur every year, and many of those are in remote areas. It's very destructive if they're near major population centers, because what happens in population centers, you're going to have the shaking of the ground. Ground could also undergo what we'll talk about later. It's called liquefaction, where it basically turns into a liquid, and you hear about the idea of quicksand. Well, essentially that's what ground liquefaction is. And water lines and gas lines break, which can cause fires. So we'll talk about one of those examples in 1906 for the San Francisco fire. And to give you actually a picture, so this is the San Francisco fire here. You can see the fire off in the distance here, and all the people watching, and you can see the destruction to the buildings. So normally I will post the actual lecture online, but there'll be a link here to earthquakes in the last week, and I'll try and remember to show that to you guys when we get back. So reasons for these sudden energy releases. One is atomic explosions. Another one is volcanic eruptions. And then the major one are faults. And I would have had this in bold, so remember, faults are these large fractures in the Earth's crust. It's usually associated with plate boundaries, but faults can also occur in areas where there's stress that has caused cracks in the Earth's crust. Also remember when we talked about the fact for our transform fault, so if this was our mid-ocean ridge, transform fault, mid-ocean ridge. So this is going in this direction, this is going in this direction. Remember we have these lines that continue out, these inactive portions. These inactive portions are old scars that continue to be there, and because of the fact that they are cracked, you can get earthquakes along them. And so I'll talk about some examples of that in a little bit. One of the things we discovered is, and I'll give you just a case study here. So in 1962, Denver experienced frequent tremors. And this is Denver, Colorado. It's in the center of the country. It's nowhere near a plate boundary. And it was a result of actually injecting waste into the ground. And this waste made its way into a buried fault line, and it caused it to have slippage. And we've been seeing this more and more as they've been doing this, what do they call it? Why has the name escaped me now? It's injection wells that have been taking place, fracking. Areas where fracking is occurring, those areas now are experiencing higher rates of earthquakes. They're relatively small, but like Arkansas is now one of the areas that has more small earthquakes than California does. And California used to be a big state in the United States for earthquakes. So it's an interesting situation. Here you can see this is, these trees used to be in a straight line, and you notice this area here where things moved. Here you can see a fracture line that has formed across a road. So this is an image of California, and all of these red lines are fracture zones. This is actually a plate boundary right here. I'm not quite on my line here, but this is the San Andreas Fault. So that's an actual plate boundary. But all the others are little fracture zones. Most of these are not perfectly straight, and they're usually locked in place by what we call confining pressure. The overlaying crust is holding it in place. And they can lay inactive for thousands of years and still become active again. So, for instance, in Virginia, there was an earthquake in August of 2011. There have been earthquakes along the Mississippi Valley. Charleston had an earthquake in 1886 that we'll talk about a little bit later as well. So, causes. So we're going to talk about this guy. His name was H.F. Reed. And H.F. Reed conducted a study following the 1906 San Francisco earthquake. So he found that the Pacific plate had lurched 4.7 meters, and that the crustal pressure over hundreds of years had led to these crustal rocks actually being deformed. They'd been storing up energy over time, and eventually they just reached the point where they can't take the stress anymore, and they move. And when they move, they release a lot of energy, causing the earthquake. So this is H.F. Reed right here. And notice this huge crack in the earth that runs all through here. And that is the result of the earthquake. So here we have a fault line right here. And what happens is over time, you have these rocks are as these plates or even within one plate, you have a little bit of stress that is starting to form. Think of, I don't know if any of you have brothers or sisters, but there's that little stress that starts to pick up between the two of you every so often, and eventually you explode at each other. Well, it's the same basic idea. You have some stress taking place, usually because of movement, and things start to bend a little bit, and it gets uncomfortable, and eventually it just can't take it anymore, and you get the slippage. And at that point is when you're releasing a whole lot of energy. And so you can also look at the example of a stick. If I brought a stick in and I slowly started trying to push the edges, you would see the stick would bend and bend and bend, and eventually it just won't take it anymore, and it snaps. And then at that point, you hear the pop. That is the release. And so in our particular case, that is the release of the seismic energy that's heading out in all directions, causing the earthquake. And once that strain is released, sometimes you get a bunch of little earthquakes that occur after that. So the book has a really nice summary for it. It says, earthquakes are produced by the rapid release of elastic energy stored in rock that has been deformed by differential stress. Okay, so I'll say that again. Earthquakes are produced by the rapid release of elastic energy stored in rocks that has been deformed by differential stress. So when earthquakes occur, the main quake lasts for less than 1 minute. Sometimes, and this would be on the screen if this was behaving, small quakes precede, which means that they come before a major earthquake. And these are called foreshocks. And foreshocks can occur days or even several years before a major earthquake. There's no clear definition of when it is a foreshock and when it is a separate clump of earthquakes, so please don't ask. Additional movements following a major quake are called aftershocks. Okay, so these can come after an earthquake. They're usually weaker than the original quake, but they can destroy a badly damaged building, and they generally diminish in intensity and frequency over several months. Movements can occur along this and other adjoining faults. In some cases, they can be really large, and you can have over 100 a day for the next week. So it's just picture you've gone through a major earthquake, there's a lot of damage, and then for a week, every day, you can have 100 earthquakes. It's the additional stress on top of it all. And so then more and more buildings are coming down. And so I have a link here. If you look at my original PowerPoint, I really want you guys to look at. It's 1 week of foreshocks and aftershocks that are associated with the Japan quake. And so do take a look at that. You're going to really see everything that Japan went through and just how devastating that earthquake really was for them. So here we have seismology, and seismology is the study of earthquakes. And technically earthquake waves, which you could also put in here seismic waves. So this here is a picture of a seismograph. Remember we talked about that? That's an instrument used to record seismic waves. And it dates back about 2,000 years. And so the way this works is you have a piece that is embedded in the bedrock, and you have this little string that is attached to it. So as this bedrock moves, the string is going to vibrate, and that string runs all the way up, and here's the wire and a little pivot point. And so when it vibrates, it's going to shake a lot. If it's not vibrating, it's going to stay straight. And so we measure these, and we'll look at these. So this image here that we see here is called a seismogram. It's the record that we get from a seismograph. So seismogram. So let's look at some seismic waves that are the result from this release of energy. There are two main types of seismic waves. There are these waves here. Okay, you notice how they look different. These are our surface waves. They're also, ooh, boy, that was a terrible writing job, guys. I am so sorry. I'm trying not to accidentally press other buttons, which, by the way, I have a couple of times. These are also referred to as L waves. And they travel around the outer layer of the earth, so the surface of the earth. Their motion is very complex. They can cause the ground to move like an ocean swell, where the water moves up and down, but here the ground is moving up and down. But it can also cause the ground to move side to side. And this is extremely damaging to the foundations of structures. This is really what causes buildings to collapse. Now, all of these others are called body waves. And they travel through Earth's interior. There are two types. There are P waves and S waves. So these are primary, or P waves. And they push things together and then pull them back apart. Okay? So it's like shaking a person or the workings of vocal cords. You can use a slinky and just move your slinky back and forth and back and forth. Not up and down, just straight back and forth. The thing with primary waves is that they can move through solids, liquids, and gases. Okay, so they can move through a lot of different types of material. These are our S waves, also referred to as secondary waves. I'm going to move this over here so I have space. And These shake the particles at right angles to the direction of travel. So if my energy is going in this direction, my waves are going to go in this direction. Okay? This only changes the shape of the material that transmits it. And because it's only changing the shape, it does not work for liquids or gases because they don't resist a change to shape. So these secondary waves only move through solid material. And this is going to be important in our discussion a little later on, okay? So if you take your slinky again and now you move it up and down, that is your idea of your secondary waves. So this is just another example of that. Here I've got my slinky here, and it's going to go in this direction, see my compression. And so you can see this wave as it moves through. So this is our example for our primary waves, or P waves. Here is our rope at rest. Here we have, we're shaking it and you can see this movement and it travels through. And this is our example for our secondary waves, or our S waves. And notice the difference in the types of damage that we get. We get these cracks that form here. We have our lines broken. With our S waves, we don't have lines broken. What we do is we have this sort of weird swelling movement. So I want you to notice the difference in the shape of these waves. P waves come first. Because they travel faster. They travel about 1.7 times faster than these waves. Okay, notice that these are a little bit larger. Surface waves are really large. And so these are 10% slower than the S waves. So they arrive last. So it's always first, second, third. Always in this order. The actual velocity depends, though, on the material that the waves pass through. And we'll talk later about why this fact is important. What's to know is the higher the amplitude, in other words, the bigger this is versus this, the greater the destruction. So if you look at this, you notice that this has the greatest movement up and down. So our surface waves cause the most damage, just like we talked about earlier. So I will review this a little bit when I get back because this is a slightly difficult conversation to have. But how do we locate an earthquake? We can use the difference in velocities of the P wave and the S waves to determine the epicenter. The greater the distance between our P waves and S waves, the further this seismograph was from the epicenter. So if we notice here, first P wave, first S wave, hopefully you can see the fact that this one is the closest and this one is the furthest away because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and a half minutes. Seconds, 10.5 seconds. Oh, that is minutes. Never mind. Minutes. Here it's 1, 2, 3, 4, 5, 6, 7. And here it's 1, 2, 3, 4, 5. Okay? So think of it as race cars. Um, you probably hated these examples when you were in school. I know it was not my favorite example in school. So you have two race cars. One race car is traveling at 45 miles per hour. I know that's not very fast. Another race car is traveling at 90 miles an hour. In when they reach their destination in 40 miles, how many miles apart are they? Or how long did it take them to get there? How many minutes would it take them to travel 60 miles? So you can do that calculation. This is the same basic idea. Depending on the material, because of how far it is, those P to S waves are going to take longer if I do it 40 miles than if I do 100 miles. Okay, it's the difference between their arrival is going to be larger. So it's the same basic idea. So, trying to figure out where I am. So, let's keep in mind Nagpur, India. This is a 5-minute difference. We're going to look at this next thing. So now we take that and we go to this diagram. You need to know how to use this on an exam, which is why I'll review it again when I get back. So this is the distance traveled by a P wave, and this is the distance rate traveled by an S wave. So I have distance here in kilometers or distance in miles, and here's my time in minutes. So I have 5 minutes. If I did this, if I took 5 minutes and I came across here, then which one do I pick? The S one, which would be, 1200, or do I keep going over here and come down, which is 2500? No. I'm erasing this. This is a big no. Please don't do that. Because we are looking for the difference in timing between the P wave and the S wave. So what we have to do instead is to figure out a 5-minute time interval between these. So if I started here, like right here, this is 2 minutes, 3 minutes, 4 minutes. So this is 2 minutes. So this is a 2-minute time interval. So that's not a 5-minute time interval. So let's come here. I have 1, 2, 3.75. 0.75. That's not a 5-minute time interval. So I would keep moving up here until I find a 5-minute time interval, which is right here. See, I have 1, 2, 3, 4, 5 minutes. And so this is about 3,500 kilometers or 2,100 miles. Okay? So that would be for Nagpur, India. And then we would do that again for the other locations, which obviously this isn't large enough to be able to do. So this tells us how far our location in India was, but it does not tell us anything more than that. It gives us a radius. So we need at least 3 seismograph recordings. So here is our Nagpur. It was 3,400, so pretty close to my 3,500 estimation. So you draw a circle all the way around 3,400 meters from it. For Darwin, it was 4,900 kilometers. So you draw a radius all the way around at 4,900. Now you have 2 potential locations where they overlap, here and here. So that's why you need your third, which is Paris, which was 8,200 kilometers away. So I'm going to draw this one in, and look, this one doesn't overlap, this one does. So this is the location. This is the epicenter. This is our focus. So on an exam, I'm just going to have relatively simple ones. I just want you to you're not going to do a full explanation for any of this. In lab, you will. But on the exam, all I want you to be able to do is to use that graph, to just be able to answer simple questions using the graph. And understand that the distance between the P and S, the further apart those are, the closer it was. Sorry, the further it was. The closer together those P and S waves are, the closer it is, okay? So just understand that concept. So now we know where it was located. So this is a map of the distribution of 14,229 earthquakes with magnitudes greater than 5.0 from 1980 to 1990. And 95% of the earthquakes originated within a few narrow regions. So I want to identify them. The first one is this one. This is our circum-Pacific belt, also sometimes known as the Ring of Fire. So here, if you'll remember from our discussions on plate boundaries, this is where subduction takes place. And areas of subduction oftentimes have a lot of earthquake activity. Another belt is along the oceanic ridge system. Notice all of these are oceanic ridges. And you see all of these earthquakes that form along them. And then lastly is this area. This is the Alpine Himalayan belt, where two plates, or actually three plates, are colliding into each other. This is the Indo-Australian plate. This is the, this is the European plate. And we've got an Arabian plate here and our African plate. So I guess there's really four of them. And so we've got land associated here. And so this is an area where there's a lot of earthquakes. So I'm going to end it here. When I get back, I'll do a quick review, and then we're going to look at how we describe the size of earthquakes. As soon as I can, once I get all of these loaded, then I will post an extra credit quiz for you guys, and I'll let you know when that's ready. So take care, everyone, and I will see you all soon. Bye.